Hello students, hope you are doing good. Welcome to our next module that explaining the ionic polarization. So already I told you, suppose you take the material and place in between two parallel plates, and the purpose of placing this dielectric material, you know that dielectric material is an insulating material. That may be the mica, glass plate, paper. So such a kind of non-conducting materials are placed between two parallel plates so that the charges induced at the parallel plate again induced at the insulating material like dielectric material, so that the charges can be charged, means storage of charges takes place in the dielectric materials. So that is the purpose of the application of the dielectric materials in capacitors, supercapacitors, and storage devices, and so on. Suppose the dielectric material consists of the ionic molecules. So what will happen when you apply the external electric field? What is called this external electric field? Always we are telling that applying external electric field. So what is this? So this is nothing but that is when you connect the biasing, means positive charge and a negative charge, means potential between two parallel plates, right? So proper functioning of that is accelerating this electron towards a positively charged plate, and the positive charges tends to move towards the negative charged plate. So we have to apply the external electric field. That is what it is called as external electric field, E. So that is what we are applying. That is the direction of applied field. That is, the positive charges will move once you started applying the external electric field, and the negative charges will move away from the direction of the applied field, right? So just imagine the system consists of two ions. Say for example, you take sodium chloride, sodium positive charge, chlorine negative charge, right? And you can place these positive and negative charges. Let us consider these are the parallel plate capacitors, right? So plate 1 and here plate 2, and you are applying the external field, so that these are the positive charges accumulated at this electrode, and the negative charges will accumulate this electrode, right? So this one is anion that have the positive charge. That's why it is moved towards the negatively charged plate, right, when you apply the electric field. And so before the application of the electric field, these charges, means cation and anion, very close to each other. And when you started to apply the external electric field, this positive ion moves towards the negative charged plate through a distance of x2. And this negatively charged ion, means let us say chlorine, moves towards a positively charged plate, and it traverses a distance of x1, right? And once you apply the external electric field, because it's a very quite natural phenomena, once you apply the force and tends to bring these two charges apart from each other, means you are going to pulling these charges away from each other, no, right? Obviously you can find that by the application of the potential field, you can say that it is a Lorentz field or Lorentz force that tends to split these two charges away from each other. And already we have seen that in the case of the electronic polarization, once you apply the external field, the Lorentz force tends to fetch away these positive charges and the negative charges from its equilibrium position. Here also, once you apply the external electric field, the anion and the cation will move away from the equilibrium position, and it is unstable because we are acting against the nature of this bonding of both the anion and the cation, right? So what will happen once you apply the external electric field? The restoring force will act, that it tends to bring these two charges towards each other and place these two charges at the equilibrium position. Okay, and you can write the force acting on the ions, that is in general you can write F equal to, that is a restoring force, right, E into E, or you can write that is equivalent to mass into angular frequency omega naught into the displacement. So you can write that is E equal to, you take these two components, right, you leave that this F, and you can have E equal to m omega naught square x, right, where m is the mass of the negative charge electron or positive charged ion. It's a common equation, right? This one is a displacement, angular frequency, mass, electronic charge, and applied electric field capital E. And in general, you can take x equal to E by m omega naught square, and let us take here m is the mass of an electron and capital M is the mass of a positive charge. Because positive charge is heavier, let us take that as denoted by the capital M, so that you can write that is in general you can write to say, for example, here you substitute x1, that is x1 equal to E divided by m small m omega naught square. In a similar way, suppose you are having for the negative positive charge and you write the suffix here x2 and that equal to E divided by capital M omega naught square, and these three components are same for both the positive and the negative charges, and the only differs among them is mass, that is small m and capital M, so that you can write the sum of these displacements x1 plus x2 equal to E divided by omega naught square, and these are the individual quantity, that is 1 by m plus 1 by capital M, and these are the common term for these two charges. And you know that is ionic polarization is equal to product of any of the charge and the displacement, right? So any one of the charge you can take that as E, and you know that already x1 plus x2 equal to E into E divided by omega naught square 1 by m plus 1 by m. Here already E is there, so multiplying you can have E square E divided by omega naught square 1 by m plus 1 by capital M, or already you know that is ionic polarization equal to this ionic polarization is directly proportional. Once you take this E in the left hand side, and this one is proportionality constant, and you can obviously note that mu ionic means ionic polarization is directly proportional to this external field E. So field is increases, ionic polarization also increases, means the separation of these two positive and negative charges will be increases. And equating this one, you can have the proportionality constant, that is alpha ionic means ionic polarizability, and that equal to mu ionic divided by E. But you know that already mu ionic, the equivalent term is E square omega naught square into E. Here it comes 1 by m plus 1 by capital M divided by this E. So cancelling these both E, you can have finally E square divided by omega naught square 1 by m plus 1 by capital M. So this polarization can occur at the optical frequencies like 10 power 13 Hz infrared, and it is slower process compared to electronic polarization, because the heavier there you can find the electrons and the positive charges. Here the ions are responsible here. The weight of these ions are more, so that this is a slower process, right? And it is independent of the temperature. You can find that there is no temperature term in this equation. So ionic polarizability equal to E square by omega naught square 1 by m plus 1 by capital M, right? Got it? The next kind of polarization is orientation polarization. In the case of orientation polarization, let us take the polar molecules like water molecules, and this one is the before the application of the external electric field. You can find that this H2O, right? H has the positive charges, and the water molecule, 2 hydrogen atoms are there, and there is a heavier oxygen atom have the negative charge, and this plus and here plus 2 plus charges are there, and this oxygen, and this one is a vector component. And before the application of this vector component, you can sum up all these vector components, and finally you can have the zero value of polarization, because these are randomly arranged, right? You can see that this is arrow directions, that is called indicates the vector directions, right? So once you apply the external electric field, what will happen? These positive charges tends to align towards the direction of applied field, and these negative charges tends to move away from the direction of the field, so that you can have the group of these two system of ions, that is rotational field, rotation of these molecules takes place, and this is called as orientation polarization. It means orientation, rotation of this molecule takes place due to the application of the external field. So this one is orientation polarization, and its frequency of occurrence is from 10 power 6 Hz to 10 power 10 Hz, and it's a slow process compared to ionic polarization, and because more torque required to rotate these polar molecules, and it is depends on the temperature, right? And it contributes very means 1 part in thousands of value of the polarizability. So it does not have the contributed value of the polarizability, so can leave from. And for the expression for the orientation polarization, you can find that alpha naught means polarizability equal to mu square divided by 3 kT, right? It has the temperature component, so it depends on the temperature. So temperature increases, the polarizability decreases, because it is present in the denominator. So total polarizability alpha equal to alpha electronic plus alpha ionic plus alpha orientation, that equal to, you can write to 4 pi epsilon naught r cube. It's already you have derived, and this one also derived, and this one, and the summing of these all components are called as the Langevin-Debye equation for total polarizability in dielectrics. Thank you. See you in the next module.